everybody. Very good evening and a warm welcome to Enlite. How are you all? How are you all? Please let me know if I'm audible and visible. Again, I can't see myself. I only can see the chat. What's up? What's up? Nobody's responding. Hello? Okay, I think I'm visible, right? Can you give me a thumbs up if I'm audible and visible? Because I really have no idea if I'm audible and visible. Audible and visible too. Thank you, Kaushal. Hi, Srinath. I'm good. I'm good. How are you all? Are you all doing great? So the studio has changed, and that's why I might be looking shorter because my actual height is short. But in yesterday's studio, no, the camera was a little, was a little down, so you could see me a little bit more. But today, if I have to be on my toes. I'll have to be on my toes if you want to see me a little more, right? Yeah. Or maybe I'll have to stand somewhere else. So I'm actually just 5'2", and it is a great difficulty sometimes, especially in the studios, because some of your the male teachers especially, have you seen Wasim sir, Shimon sir, Shreyas sir? They're like really super tall. They look like they're pillars. So anyway, all right, forget about all of that. So everybody, a warm welcome to Vedantu Enlite channel, and today we are going to read about periodic properties exceptions. In the last session, we spoke about the trends of periodic properties, and today we're going to talk about the exception. Hi Nilu, hi everybody. I do remember you guys. Yes, I do remember you. Hello. Okay, all right. So today, what exactly are we going to learn, right? Let's talk about that. Let's talk about that. Okay? So because you all are here already, please do like it. If you like the way I teach you, then do not forget to like it. And if you like it, then please do tell your friends also to, share it with your friends and let them know that here we are teaching you, JE and NEET completely in English, right? So it will be beneficial for everybody then, okay? Now you already know about me. I have given my introduction in the last session also, but just so that if you just if you want to know a bit more, then here it is. Yeah, my name is Nabamita. How is it pronounced? It's pronounced as Nabamita because I'm a Bengali, right? And I am a master teacher of chemistry for this segment here. Before getting into this whole teaching field, I was a research associate in IIT Guwahati. I have completed my master's in nanoscience and technology. I have also completed my bachelor's in education. So basically, I'm a trained teacher and I can teach you in government schools, but I guess Vedantu is more fun, right? Yeah. Apart from that, right? My favorite food is biryani, and I love to travel and like sleepy. I'm mostly sleepy. Trust me, all I want to do right now is for this weekend, Saturday and Sunday, my plan is to just sleep. That's exactly what my plan is. I love sleeping. Anyway, moving on from there. So let's start. Yes, can you tell again your name? My name is Nabamita. What is it? Nabamita. It means new friend. So I think that's how it is. I'm a new friend, right? Yeah. Can you come to Vedantu Master Tamil? But I do not know how to speak in Tamil. Tamil Teriyad. I told you yesterday. I do not know how to speak in Tamil. So how am I going to teach you in Tamil? I can only teach you in English and Hindi. So that's what I'm doing. I'm here to teach you in English. Okay, let's start, everybody. Shall we? Everyone ready? Let's begin today's session. Okay? Cool. So let's begin with the exceptions. Now, see, one thing that is very, very important is, people talk about chemistry, the mystery of chemistry. Do you know half of the mystery of chemistry actually comes from the exceptions or the anomalies, right? And if you can logically explain the exceptions or the anomalies, I think half of your mystery is solved. You do not have to say that mysterious chemistry and all of that, right? Yes. Singam, you think so, but I think it's going to take me a lot of time to learn Tamil and then teach you in that. Anyway, let's learn in English. So today the first exception or the first anomaly that we are going to read about is atomic radius. Now, if you remember in the last session, in yesterday's session, when we were reading about the trends, we got to know that across the period, right, when you go left to right, across the period, what happens to the atomic radius, everybody? Can you tell me? Yes. What happens to the atomic, this thing? What happens to the atomic radius? Please go ahead, let me know. Left to right in a period, left to right across a period, what happens? The size decreases, correct? The size decreases. No, Singam, I'll tell you about that. Don't worry. Yes, the size decreases, correct? Why does the size decreases? Effective nuclear charge increases, so the nucleus is able to pull the electrons very strongly, right? So we can say here that size decreases, okay? But did you know that we are able to see one twist? One twist is seen here, okay? What is that twist? What is that twist? The twist, my dear student, is you are going, right, from group 1 to group 17, right? You go, right? You see that size decreases, 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 and then suddenly there is a sudden increment in the size when it comes to the noble gases. Why is that so? Why is that the noble gases, they have the bigger size? Well, again, now if you remember the trends class yesterday in the last session, yes, in the last session, what did I teach you? There are 4 types of atomic radius, correct? What are the 4 types of atomic radius? There is covalent, there is ionic, there is metallic, and there is van der Waal, correct? Yes, everyone, right? Do we remember this? Now we also read there that the van der Waal radius is actually the biggest. Yes, and the covalent was the smallest. Now, in noble gases, you know that it is the van der Waal radii that works, right? So, can we understand from that explanation, can we understand that yes, the noble gases will have bigger radius? Is this clear? This explanation is clear. So, this mystery is just goes away. Weak forces. Absolutely right, Kaushal. Absolutely right. Muthu Kumar, how to become strong in inorganic chemistry? Keep attending the classes and do write it down. Whatever I suggest, whatever I say, no, write it down. Hi, Sharon. Hi. Welcome to the class. Guys, did you tell your friends or not to come to the class? I see a huge dip in the number of students today. Yesterday, there were a lot more students, yeah? Do share it with your friends, okay? Anyway, all right. Now, that's not all. In case of atomic, I will send you. Yes, I have spoken to our channel manager and I will send you the PDF. Pakka promise. I think by Monday, both this as well as the previous session PDF will be uploaded, okay? I will start 12. Next will be 12. Next, we will start with coordination compounds, okay? Next, we will start with coordination compound because I understand that that's probably one of the toughest topic of class 12, right? So, we will start with that. When will you go for organic? Mukund, I'm not, I'm not taking organic. I'm only taking inorganic chemistry right now. Organic will be taken by Wasim sir. Okay? All right? Yeah? Okay. So, moving on. Everybody, focus up. If we don't focus, then we get deviated from the class and then we only talk about other things and we forget about this. Right? Okay. Come back, focus up, everybody. Yeah. So, that's not the only exception or that's not the only anomaly in case of atomic radius, right? We also see some more exceptions, right? Let's talk about the group 13. Okay, let's talk about the group 13. Okay, group 13, that is the boron family, correct? So that means what do we have? We have Bal Gangadhar, Indian Tilak, right? Indian Tilak, okay? That's how I remember it. If you want to learn it some other way, that's also fine. So it is boron, aluminium, gallium, indium, and thallium. Correct? Now, what do we expect? We expect and we know that in a group, the atomic size decreases. The atomic size increases, right? That's what we know. So that means we would expect that it should be like this. Right? That means we expect it to be what? We expect that this will be the biggest, correct? This will be the biggest, right? And we expect that this will be bigger. Aluminium will be bigger than boron. And we expect gallium to be bigger than aluminium, correct? Right, everybody? Yes? Take a look at this place. Here, this 3. Okay? Alright, this 3. We expect gallium to be bigger than aluminium, but you know what? That doesn't happen. We see that aluminium has a bigger size than gallium. Why? Why? I'll tell you why. In case of gallium, what happens? The D, yes, 3D gets into the picture. What happens? 3D gets into the picture. Yes, no idea, Kaushal, no problem, I'll tell you. So let's write the electronic configurations, है ना? Let's write the electronic configuration. For this, I will have to write Ne, and then what will be the electronic configuration, everybody? I have written Ne. Then after that, what do I have to write? I will have to write 3s2, 3p1, right? Yes, correct, everybody. Now, if I have to write the electronic configuration of gallium, then what am I going to write? Hello, Lalita. Please focus here, bacha. Please focus here, okay? For this, I will have to write, see, 1 second. Here, let me write it down here. For this, it will be argon 3D10 4s2 4p1. Correct? Am I right here, everyone? Am I right? Is this correct, everybody? Yes? Is this correct? Now take a look at this 3D here. Now what do we know? Do we know that d orbitals have even poor shielding effect? So because of poor shielding effect, do we understand that again the nucleus will be able to pull the electrons closer? So can we now understand why aluminium has a bigger size? Yes, why aluminium is of a bigger size than gallium? Is this mystery clear? Is this mystery clear, everybody? Yes? Getting it? Cool? All right. Now, one more thing. Now, what do you expect? See, what do you expect? You would expect that indium and thallium, see, here, 3s2, 4s2. Now, here it will be what? 5s2 and then 6s2. See, one whole shell is increasing. So, you would expect that the size of thallium would be really, really big. But is that the case? Again, that's not the case, okay? Again, that is not the case. We see that indium is only 167 picometer, whereas thallium is 170 picometer. Why? Only this much difference. Why is it only this much difference? 167 and 170 picometer. Why? One more reason. Can we guess? Can we guess, everybody? Any guesses here? Why is this happening? Any guesses? Why is this happening? Anybody? Yes? Shri Harsha, I will repeat, bacha. I will repeat again. Yeah, just focus right now here. I will repeat it again. Okay? I'll tell you. In this slide, whatever. Now, caution. Here, what happens is the F14. F14 enters. F14 has even poor shielding effect than D. And that is why there is not much increment in the size. Clear? This is fine? Is this fine, everybody? Clear? Now, another exception, okay? Another lanthanide contraction, we are coming to it, okay? This is all clear? All right. Now, what we're going to do is we are going to take the 3D series. Okay? We are going to take the 3D series. Okay? What is your 3D series? Your 3D series is basically scandium, titanium, vanadium, and then what else? What else are there? Scandium, titanium, vanadium, chromium, right? Chromium, manganese, then there is iron, cobalt, nickel, yes, copper, and zinc. Okay? All right. Less space, I'm not able to write it. But do you understand? Yes? Do you understand this? Yes? Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, zinc. Right? Again, everybody, do we understand that as we see left to right across a period, the size should decrease? The size should decrease. Yes, but what happens? What happens? We see that the size decreases till here. Till here, the size decreases. But then from here, we see that the size almost remains same. The size almost remains same. Why? Because there are two things that are happening. One, effective nuclear charge increases. Yes, all right. But because in the same shell, more and more electrons are adding up, there is also interelectronic repulsion. Yes. Now, when these two are together working here, they kind of balance, and you see that the size do not really decrease much. It remains the same. And in case of zinc, it increases. In case of zinc, it increases. Because of what? Fully filled d orbital. And here also in manganese also you see half filled. Okay. Here it is half filled. Correct. And here you see that it is fully filled. Alright. So what are the things that we have learned, everybody? What are the things that, is this all clear? Hi Shreya sir. Guys, Shreya sir is also here. Ekdam acha, Shreya sir. I'm absolutely great. Shreya sir is also here. Okay, so everybody, what are the three things that we have understood from here? From only one single slide, we have understood three exceptions, right? First of all, that atomic radius general trend is that left to right size decreases. But what do we see? We suddenly see that in case of noble gases it increases. Yes, that we understood. Repeat the last one. I will. Okay. Then we understood for group 13. Yes, for group 13, what did we see? For group 13, my pet name is Nabamita Ma'am. Right? Then again in group 13, we saw that we expect gallium to be bigger than aluminium, but that's not the case. Yes, we see that aluminium is bigger than gallium. Why? Because of D. Yes, D orbital, these electrons being present here, what do we see? Poor shielding effect. Size decreases for gallium, and for aluminium that increases. Correct? And the same thing we have seen here also. There is not much increment in from indium to thallium. Why? Because of F14. Yes, do we understand this? And then we took the case of 3D series: scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So we expected that left to right size will decrease, but we saw that in here the size almost remains same. Why? Because two forces, effective nuclear charge as well as inter-electronic repulsion. Yes, because of those two balancing each other, we see that there is not much difference. Am I clear, everybody? Yes, is this slide clear? Thank you, Shreya sir. Yes, Lalita Patel, absolutely right. Is this clear? Shall we move on then? Shall we move on? Shall we move on? Clearo, absolutely clearo. Give me some thumbs up, everybody, so that we can we can move on from this slide. I will, Pranish. Next class will be about coordination compounds only, okay? First, we are just doing the exceptions and the trends, because a lot of questions in JEE as well as in NEET, trends and exceptions are, a little confusing. So there are a lot of questions there. And that is why I'm doing it first. After that, we will do coordination compounds, okay? Shri Harsha, what is it that you did not understand? We are talking about, Asha, you understood. You have retracted the message, huh? Thank you so much, Shrey sir. Okay, I can see thumbs up. Let's move on then. So this is basically just the explanation, which I have already explained. This, when you get it as a PDF, I think it will be beneficial for you. But right now, I have already explained it. Okay. All right. Okay. All right. Thank you, Parma. Thank you so much. Yeah. Okay. Moving on to the next one. Now let's take a look at it. Okay. Now let's take a look at it. So see here. This is your F block. In the last session, we did not touch the F block at all, right? We did not speak about lanthanides and actinides at all, right? We completely forgot it. But today we are going to touch the lanthanides. So in case of lanthanides, what happens is we see a very nice decrease in the size, right? A constant decrease. It just keeps decreasing, decreasing, decreasing. What is the decrease? What are the synonyms of decrease? What are the synonyms? Contraction can also be a decrease in the size. Lalita, where are you going? Huh? Don't go. Yes. What is it? Contraction. So that means what? Lanthanide contraction. Right, everybody? That is your lanthanide contraction. So basically, once again, everybody, as you all know, yesterday we read about shielding effect. Remember that accident? Two cars collided with each other. Then you can't see. But if it is F block, see, if it is F orbital, then what will it be? It will be like this. It will be somewhat like this. Not able to draw it very properly. But see, you have so many spaces, right? You have so many spaces from where you can see the accident, correct? Isn't it? Yes. Poor shielding effect. Poor shielding effect. So if there is such a poor shielding effect, obviously the nucleus will be able to pull the atom. The nucleus will be able to pull the electrons. And that means that the size will keep decreasing. And that is your lanthanide contraction. Okay, that is your lanthanide contraction. This is easy, right? This is easy. Do we understand lanthanide contraction, everyone? Do we understand it or no? Hello, hello. No one is responding only. Should I stop the class? Come on, guys, tell me. Do we got it? Yes, yes, absolutely. No, who did not understand? Yes, this only occurs in the last block. Yes. Yes, absolutely. Peria, semi, what are you asking, bacha? Did not understand. Okay, let's understand this again. So, shielding effect. Shielding effect, do you remember? In the last session, I taught you shielding effect, right? What is shielding effect? Shielding effect is basically, yes, how much are the other electrons, how much are the other electrons crowding up so that the last electron is not getting any force from the nucleus. Huh? Are you understanding? So what example did I give you? The example that I gave you was, imagine two cars have met with an accident. Okay? No, this is not a repeat batch or anything, Peria. This is just me teaching you. We have just started with inorganic chemistry. The car accident, do you remember? Now, if there are too many people around and you are here, will you be able to see the accident? Will you be able to see the accident? Yes, Tejaswini explaining it. Will you be able to see the accident easily? No, because there are already too many people who are crowding this place. Right? Yes, correct? Absolutely. But what if I remove some people from? If I remove some people from here, now will you be able to see the accident? Now will you be able to see the accident? You will be. Correct? Now you will be able to see the accident. The same way, if I consider this is my nucleus, right? Now, if I have electrons, then here is another electron. Do you think that the positive charges in the nucleus will be able to pull this electron easily or not? Because there are so many electrons, this electron will not be experiencing much of the force, right? And that is your shielding effect. Okay, that is your shielding effect. Basically, these electrons are working like an umbrella. They are protecting, okay? They are not allowing this electron to experience much of a force. And related to this, I told you what? Effective nuclear charge. What is effective nuclear charge? Basically, the total charge that this electron is facing after all the repulsion. Cool. Is this understood now? Is this understood? Now, coming to the order of sp, d and f, let's talk about it. See, now if the electrons are like this, if the electron clouds, you all know that electrons also form like cloud, right? So, if the cloud is spherical like this, do you think that this electron will be able to easily get pulled by the nucleus? Will it be or no? Will it be or no? This electron, the electron is right here and there is a spherical cloud of electron. Will the nucleus from here be able to see the electron? No, no, no. It's completely round. It's completely round, right? So the nucleus will not be able to see the electron. Great. This is your S. This is your S block, okay, or S orbital. Cool. Now when it comes to P, what do we have? We have something like this. This is the electron cloud. So if the electron is here, it can easily, it can easily be pulled by the nucleus, or if the electron is here, it can be pulled, right? Yes. So that means S has the highest shielding effect. P has a little less. Now when we come to D has something like this. Okay, D has something like C. So there is enough space, here space, here space, here space. If the electron is anywhere else, then it can be easily pulled. So less shielding effect, even lesser shielding effect in D, right? Am I right, everyone? Understanding, guys? Am I making it clear? No? Vignesh, understanding? Kaushal, Sriharsha, understanding? Yes? Huh. Now if we come to F block, see now when you come to F, okay, I'm gonna remove this, okay? I'm gonna remove this. Huh? Okay. Yeah. Now when we come to F, so this is your D, okay? Now when we come to F, see in F what happens, it is like this. Then you have, so how much space do you have? This is not exactly like this, but you know, kind of like this only. So you have space here, you have space here, you have space here, you have space here, 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 everywhere. There is space, right? So even lesser shielding effect in F. Now, F electrons are present in lanthanides. That means that the shielding effect is really, really, really poor. That means that the nucleus can pull the atoms very close. So now do we understand lanthanide contraction? Now do we understand lanthanide contraction? Is it easy? Absolutely easy, right? Come on, give me some thumbs up so that I understand and then we can move on. Give me some thumbs up, everybody. Come on. So then I'm gonna. Got it. Very easy. Great. Okay. All right. Okay. Moving. Lanthanide contraction is understood. Moving on. Now we are going to understand something that is but. Yes, Parama, what happened? But Parama, you know that this is not for you, right? I'll teach you again next year. You're only in 9th standard now. It's okay. Okay. All right. Now we're going to understand something that is very important, which is your ionization enthalpy. Somebody in the yesterday's session asked me, ma'am, what's the difference between ionization enthalpy and ionization energy? Yes. Someone asked me. I can't remember the student's name. But okay, let's understand this. Yeah, let's understand. What is ionization energy? In yesterday's session, we understood what is ionization energy. Thank you, Muskan. Thank you so much. Captain Jack, yes, you asked me. Thank you so much. Yeah. So you asked me, right? Will you teach 10th too? No, Baba. Actually, I'm already teaching 10th. Yeah, I'm actually already teaching 10th, where I'll tell you, I have already recorded the AI classes. I've already recorded the AI classes for 9th and 10th. So probably it will be live in some days that you can watch. Okay. All right. Yeah. Huh. So moving on, moving on. Yes, very good. RD has already told the definition: to remove an electron from outermost shell of gaseous isolated atom. Achha. Now, before we understand anything else, tell me something. Gaseous isolated atom. What do we mean by this term? Gaseous isolated atom. Why do we need gaseous isolated atom? Remember state of matter? States of matter, where we learned that in solids, the atoms are very close to each other. They're like, tightly tied up. Yes. Yes. And then we know in liquids, they're a little far away. But in gases, they're like really, really far away. Right? Isn't it? So when can be a molecule or an atom? When can an atom be alone? When can an atom be alone? An atom can be alone when it is in gaseous state. Right? And that is why we need gaseous isolated state. Yes. All right, we need gaseous isolated atom. So from a gaseous isolated atom, if we, no, Anubha ma'am is not leaving. She's in fact right here outside the studio. Probably she's recording for another class. No, Baba, she's not leaving. Nobody is leaving. Not me, not Wasim sir, not Anubha ma'am. None of us are leaving. Okay, we are all here in Vedantu. Don't worry. Yes. Huh. So gaseous isolated atom, we understood. Next thing, yes, we need to give minimum energy. What is minimum energy? Actually, remember in class 8, we read that we read a chapter in physics called friction. Hmm? You feel like sitting in low grades. Why? Okay, so in the lower grades, we read about friction. Remember friction? And remember static friction, where we read that the minimum force you give, right? The minimum force that you give to move a body. That's your static. That's the friction that is required to overcome the static friction. The same here. You also need a minimum energy that you give an atom to take one of its electron, right? Minimum. On top of it, if you give any energy, it will lose. Yes, but that's the minimum energy that you have to give an atom to take one of its electron. Correct? Yes, we understand this. Now, this is your ionization energy, the minimum energy given to an atom. Okay. What if I take it as a reaction? What if I take it as a reaction? I can take it as a reaction. Let's say that it is E. Okay. From E, what do I have to do? I have to make it E positive. That means I'm taking out one electron. Right? Yes. If I consider this as a reaction, that's when I will require the ionization enthalpy. What will I require? I'll require ionization enthalpy. So basically, I mean, kiddo, I think it's necessary that you learn from the basics. Okay, tell slow. Okay, all right. See, some of the students are telling me to tell them even more slow. Anyway, so this is when we require enthalpy. What is enthalpy? In a very layman term, yes, if we have to explain enthalpy, then we will say that enthalpy is basically the net heat content of a system. What is it? The net heat content of a system. Okay. All right. So we are going to understand about ionization enthalpy. All right. Now, what is the general term? This have we all understood? This have we all understood? Ionization enthalpy, ionization energy. Is this clear? Enthalpy is the net heat content of a system. And ionization energy was the minimum energy given to an atom to take one of its electrons. Understood? Great. Thank you so much. All right. Thank you. Then let me explain. Let me remove all of these. And now let's understand the general term of ionization enthalpy. Again, going back to yesterday, I remember what did I tell you? That shielding effect is the godfather of the whole periodic properties. Yes. Yes. Shielding effect. Related to shielding effect was effective nuclear charge. So what is the trend of effective nuclear charge in this thing? In the period? Effective nuclear charge increases, right? So if effective nuclear charge increases, that means that the nucleus is pulling all the electrons. That means what will happen to the ionization energy? What will happen to the ionization enthalpy? Ionization enthalpy will also increase, right? Ionization enthalpy will also increase, isn't it? It will increase. Left to right, it will increase. Now, if we take the second period, yeah, is your very on, right? Yeah. What do we expect? What do we expect? What do we expect? We expect that to increase. But what do we get? We don't get that. We see that beryllium has more than boron. Why? Why does beryllium have more ionization enthalpy than boron? Any idea? Yes, Priharsha, tell me, Kaushal, any idea? Why is this happening here? Why is this happening here? Very good. Well done. Well done. Yes, very good. Because this is filled. Because this is filled. Yes. Left to right, it will. Shri Harsha, I think you're confusing, bacha. Tell me something. Okay, understand this. Yeah. See, effective nuclear charge increases, right? More protons, so more charge, right? Now, if the protons are able to, if the nucleus is able to pull the electrons closer, then don't you think that ionization enthalpy, that is the required energy to pull one electron away will be also more. So it will increase, na? Will increase, right? Yes. This is English channel. Yes, Venkatas. This is English channel. Okay. Very good. Anyway, so do we understand? So we expect it to be, see left to right, we expect it to be increasing, right? We expect it to be increasing. Correct? Yes. Everybody, do we not expect it to be increasing? But do we see that? Do we see that? We see that? No, it's not. We don't see that. Okay. Yes. Why do we not see it? Because here you see that this is filled. See, 1s2, 2s2. But here it is only. We already know that half filled and fully filled orbitals are more stable. They don't want to change their, whatever is the arrangement. They are like, no, we don't want to change. We are fine here. We are fine here. Okay. That's what they want to do. But this is only for the first ionization energy. Now, once it has already lost one electron, right? Once it has already lost one electron, the second ionization energy again changes here. See, the second ionization energy for beryllium is lesser than boron. Got it? Yes. Hi, Marilla may do what? You want electrochemistry, sweetheart? Electrochemistry, I'm not teaching you here, okay? I'm only teaching you inorganic chemistry. My voice is not clear, guys. Are you not able to hear me? Then boron would act like beryllium. Absolutely correct. Okay. All right. And you know what? This is the same trend that you also see in case of magnesium and aluminium. You also see it in case of magnesium and aluminium. Tell me, what should you be actually seeing? What should you be actually seeing? Tell me. What is it that you should be seeing? For if I have to write the electronic configuration of magnesium, what will I write? What will I write, everybody? Very good. I will have to write 1s2, 2s2, 2p6, 3s2. है ना? See, 1s2, 2s2, 2p6, 3s2. Right? Yes. See, filled. Right? But is that the same case for aluminium? In aluminium, what do we have? The last one we have 3p1. So see, there you have your answer. Okay, now another thing that you see is again nitrogen and oxygen. Nitrogen and oxygen also you see the same thing. See, nitrogen and oxygen also you see the same thing here. Same you see, okay? In case of nitrogen also, what do you have? 1s2, 2s2, 2p3, right? What do you have? 1s2, 2s2, 2p3. See, half filled. This is half filled. Yes, this is half filled. So here also you will see the same phenomenon. Got it? Understood ionization enthalpy? Is this clear? Half filled p orbital. Absolutely right. And one more. One more you have is phosphorus and sulfur, I think. Yes, phosphorus and sulfur also you will see the same thing. In case of phosphorus and sulfur, phosphorus and sulfur. Phosphorus and sulfur. Yes. Okay. All right. Shall we move on then? Can I have some this thing? First send questions, ma'am, please. Questions of what? I will take care of questions, beta. But how will you do questions first if you do not know the concepts? Yes? How will you do the questions if you do not know the concept? First, you have to understand the concept, then we will do the questions. No? Yeah. Then we will do the questions, isn't it? Okay. Alrighty then. Moving on. Yes, moving on. Oh, this I have already told you. See, nitrogen and oxygen I have already told you, right? Yes, explain this. Okay, explain this as well. Now we will go to electron affinity. How many of you remember the example of electron affinity? I need to drink some more water. Yes. How many of you remember electron affinity yesterday? So, how to compare N and O? Acha. Let me tell you. Here. See, N has half-filled orbitals, no? 2p3. And we know that half-filled are more stable. Okay? Alright? And we know that, see, in oxygen it is 2p4. That's how you compare. Okay? That's how we compare. We're talking about the second period. Got it, Soham? Acha, N and O plus. N and O plus here. See, after losing one electron, When oxygen attains electronic configuration of N, then the second ionization of O will be more than nitrogen. Here. Got it, got it. Yes, I got it. See, here it is, here it is. Just taught you. Just taught you. Same as beryllium and boron. For beryllium and boron also I explained this, no? Then it comes for the second ionization energy. Second ionization energy of oxygen will be more. Okay? Cool. All right. Now we move on towards electron affinity. Yes. Okay. Let's talk about electron affinity. So how many of you remember electron affinity example? What did I teach you yesterday for electron affinity? Remember I told you that, see, as a girl, as a woman, I really love shopping, right? Like every month I have to buy something. Even during this Durga Puja sale, I waited. I've kept everything in the cart, and then once I got the sale, I was like, whoo, I got everything. But what happened? I burnt a hole in my pocket, right? I actually did burn a hole in my pocket. Lost so much money just because I shopped. So what happened? This is basically in Hindi there is a proverb, कुछ पाने के लिए कुछ खोना पड़ता है, right? कुछ पाने के लिए कुछ खोना पड़ता है. So here what happened? The electron, they want to, have an electron, but while they are getting an electron, they are also losing some energy. Do you remember this? Yes, give and take, not really, but you can. Kushal, I am actually from West Bengal, but I've never stayed there. My father had a transferable job, so we kept roaming around, and finally we settled in Assam. Okay, so basically, my mother tongue is Bengali. Anyway, so we're talking about electron affinity. Once again, coming back to Godfather, shielding effect or effective nuclear charge. Again, tell me what will happen. What is the general trend for for effective nuclear charge? Tell me, what is it? What is it? Come on, guys, be responsive. A little more interaction, please. Hello. Am I right? No one is responding. Wow. What happens to? Thank you, Kaushal. Kaushal, you are the only one who is responding. Huh? It increases across period. Okay. So what will happen to electron affinity then? What will happen to electron affinity? What will happen to electron affinity, guys? Will electron affinity also increase or decrease? It will. Okay. Electron affinity will also increase because the effective nuclear charge is increasing. That means the nucleus is able to pull more and more electrons. Obviously, electron affinity will also increase. But again, now do we see that? Do we always see that? Do we always see that? We don't. We actually don't. Where do we not see it? We see that, we do not see that in case of oxygen. No, not only that, not only that. Hey, who's saying decrease? Captain Jack, no, it will not decrease, Baba. Group. No, you guys are wrong. It decreases in a group. It decreases top to bottom in a group. It decreases across the period. It increases. Yes, right? Understanding? Understanding? Okay, now let's take the example of fluorine and chlorine. Fluorine, then chlorine comes, right? For fluorine first and then chlorine, right? Class is going to get over. Yeah, in some time. It will get over. In some time. Just a little bit more. Yeah. So you would expect that it is, what will you expect? You will expect it to decrease, right? You will expect the electron affinity to decrease. But this does not happen. Why? Because fluorine has a very chotu size. Yes, fluorine has a very chotu size. So if you try to push in one more electron, fluorine is like, no, I can't take it. I have very little size, right? Plus there is inter-electron repulsion also. So it will not allow it to go. But chlorine has a bigger size. Yes, chlorine has a bigger size. So what will happen? Chlorine will be like, cool, sure, bring it on. Chlorine will take it. Exactly. Because of bigger size here, we see an anomaly. Yes. And then what do we see? We also see the same thing with, take a look at this. We also see the same thing with oxygen and sulfur. All right. Is this clear? Is this clear, everyone? Yes. Yes. Chlorine is small. Exactly. Yes. This is clear? This is clear? All righty then. Okay. Oh, one more thing that I had to tell you was, have you noticed that Nitrogen and beryllium, they have zero affinity. Nitrogen and beryllium has zero affinity, pretty much like the noble gases. Why? This is my question. Come on. I need the answer in the chat box. You tell me. You tell me. Nitrogen and beryllium, they have zero affinity. They have zero electron affinity. Why? Just some time back only I was giving you the electronic configuration. That's where the answer is. Tell me the answer in the chat box. Kaushal, wah, wah, wah. Wah, wah, wah. Very good. They are half filled. Yes, they have half filled orbitals, and we know that half filled orbitals are very, they are what? They are like very stable, and they're like, no disturbances required. Please go. We do not want it. Yes, that's all. And finally, we come to electronegativity. Yes, we will come to electronegativity, and that's where we will end it today. Okay, that's where we will end it today. Okay. Oh, acha, this one also, this I think I missed it. The electron gain enthalpy of noble gases is positive. Why is it positive? Do you know why is it positive? Yes, it is positive because noble gases are already very stable. They do not want any electron. They do not want any electron. But if you want to give them an electron, you will have to push it in. So when you push it in, the electron gain enthalpy of the system will be positive, right? Yes. Yes, of the system it will be positive. So you will have to push it in. That is why it is positive. Very good. Well done. Yes, moving on. Last one is our electronegativity. Yes, electronegativity. Acha, yesterday's example, do you remember? Wasim sir and me, we are sharing chemistry. Yes, but does that happen with noble gases? Does that happen with noble gases? Noble gases do not want to share anything. Yes, they have no electronegativity. They are like, Baba, whatever we are absolutely fine with it, right? We are absolutely fine with it. We have no tendency to attract share electrons. Yes, they have already 8 electrons in their shells. They are like, we are stable. We are fine. They are already filled. And because electronegativity is measured in the amount of attraction between an atom and an electron, so noble gases not have any electronic. Now, is this clear, everybody? Is this session absolutely clear to you all? Any doubts? If you do have any doubts, please write it down in the comment section after the class is over. I will definitely go through the comment section. I will respond to you all, and we will have a chat or a conversation over there. Okay. And yes, I have already spoken to yes, Akhil, they are. And I have already spoken to our channel manager. I will get you the PDF as well very soon. By Monday, you will get both the PDFs. Okay. Now, the next session will be for class 12 coordination compounds. Please be there. Okay. Please be there. Also, I have a question for you. You have to tell me the answer. Ionization energy of magnesium is greater than that of aluminium. Why? I already explained to you, but please do tell me the answer. And yes, what about yesterday's answer? It was atomic mass, bacha. It was mass number, right? It was mass number. Yeah. Okay. All right. So that was all for today. That was already done. Yay. Already done. See, it's already about to be 7, right? About to be 7. Yes, it was mass number. Sunny Vlogs. Absolutely right. Now, if you want to be with me in a personal touch, yes, be with me in like if you want to personally connect with me, then don't forget to follow me on Instagram, Nabamita_Nobita. And apart from that, I guess that was all. Thank you so much. And you know what? I can tell you that I am really having fun, so much fun while taking classes here, because you all have been so welcome. I don't think I've ever met the sweetest students that you all are. Thank you so much. Can you take continue time? Hey? What continue time? That's all for today, okay? Chalo, bye-bye. See you. If you are liking the class, then do share it with your friends also. Tada. See you all, guys. Bye-bye.